This is Chapter 13, which appears on page 137 of your lab manual. The purpose of this chapter is to give you experience building functional circuits with the components that you have studied and the ones that we have available in the lab. Some of these circuits are actual machine systems being used in industry today, while others simply mimic a machine function. In all cases, you will gain valuable insight in hydraulic and pneumatic system operation. The first circuit that we're going to look at is on page 138 of your lab manual. This is called a regeneration circuit. The term regeneration refers to the fact it takes oil coming from the cylinder and sends it right back. Upon the first look at this diagram, it might not look like it'll actually work because the rod end is literally being fed back around the DCV into the incoming line coming from the supply manifold. So what ends up happening is the difference in area between the cap end and the rod end generates enough force differential that the oil, and I'm talking about the oil volume on the rod end of the cylinder, is literally forced back into the incoming flow from the pump, adding to it and into the cap end of the cylinder. So the rod end volume is literally forced into the cap end. These types of circuits only work in one direction, that's on extension. During retraction, if you can imagine the shifting of the valve, if you follow the flow path from the supply manifold through the DCV, you'll notice that a direct supply of oil coming from the supply manifold is directed toward the rod end of the cylinder, while the cap end goes directly back to tank. So in essence, the cylinder is in regeneration only during the extend stroke. During the retraction stroke, it acts as normal, but there is an increase of speed. Now, the reason for the needle valve is because the flow coming from the pump will actually impede the oil entering the DCV, so we have to slow that flow down to be able to see the full effect of the speed increase during extension. Normally, a circuit like this would not use a cylinder like we have. The cylinders that they use in these types of circuits are normally 2-to-1, meaning that the area of the piston is exactly twice the area of the rod. It should also be noted there is an excessive amount of pressure during the extend stroke. In other words, gauges A and B are reading nearly the same pressure. Under these circumstances, the force on extension is reduced greatly. The next circuit that you're going to build appears on page 140. While there are two actuators in this circuit, one of them is going to be used as an accumulator. Accumulators were already discussed. We remember their purpose. Accumulators will add volume to the circuit when needed. They can store energy. They can absorb pressure spikes. And they have many other uses besides those. In this circuit, we literally take the large bore cylinder, and by placing a spring between the cam and the bearing block, we literally turn the large bore cylinder into an accumulator. Its total volume would be calculated by the area of the piston multiplied by whatever the movement is when it's fully charged. And so in this circuit, the small needle valve beside gauge B is used to isolate the accumulator from the system so that we can see the speed of the small bore cylinder without any type of help, and we will record that speed. We were also going to notice that whenever the accumulator is functioning, that the speed of the small bore cylinder increases. You can determine that simply by watching it, and you're also going to be able to see an increase of flow rate over the flow meter. Now, if you look to the left of the circuit, right next to the supply manifold, we have a check valve by itself and a flow control valve. The check valve is used for anti-backflow to make sure that any volume coming from the accumulator does not bleed back over the top of the pump. Second, the amount of flow rate coming into the system is also controlled, and we use the flow control valve. Notice how the check valve, the ball faces the other check valve. This is to make sure that the oil runs over the needle valve and into the DCV at whatever rate we decide. That is accomplished when we're setting up the circuit and we extend the small bore cylinder. Watching it as it extends, we achieve a certain amount of flow going into the small bore cylinder. In the lower part of the circuit, flow control valve number 2 is simply a safety measure. In the event that oil should be trapped in that line for any particular reason, it can be safely bled down back to the return manifold. It should be noted that if either one of these flow controls is installed incorrectly, then the circuit will not function normally. On the one hand, you will have a leak in the system whenever you try to compress the spring. That would be with flow control number 2. And then, in the case of flow control number 1, if it is turned around wrong, you will not be able to adjust the flow rate and the speed of a small bore cylinder. When working properly, here's what we'll see. First, the small bore cylinder moves faster. Second, I can shut the power unit off if the large bore cylinder is fully charged, the spring that is fully compressed. Then we can get movement out of the small bore cylinder, thus demonstrating the ability of the accumulator to create movement in the event of a power outage. This is often an advantage for larger machines to complete a machine cycle in the event there is a power loss. This is a hydraulic automatic circuit, and it appears on page 142 of your lab manual. The operational principle of the circuit is that with a single input, an actuator will perform a complete function, extending and retracting without any intervention of the operator. The cylinder extends, reaches a limit, and then returns, and then the cycle is complete. Chief elements of this circuit include a 4-3 valve used as a three-way valve in your upper left, and that's the float center DCV, a 2-position pod operated DCV, a double acting cylinder, and a cam valve, which is also a 4-2 valve, but being used as a 3-way valve. Notice too that the unused ports are shown as blocked with the emblem X. When this circuit is assembled, the lever is pushed and oil is sent to the lower envelope of the pilot operated DCV, causing it to shift. When that happens, oil is directed into the cap end of the cylinder through the pilot operated DCV, and the cylinder extends. The cylinder continues to extend because the pilot operated DCV remains in that position until the cam on the cylinder strikes the roller wheel on the cam valve to the right. The cam valve in this manner is functioning much like a limit switch in electricity. It signals that the working actuator has reached its limit and it is now ready to return. When the cam strikes the roller wheel, an oil signal is fed up to the pilot operated DCV out of port A, and then the pilot operated DCV returns to its normal position, which is the one with the lines connected to it. The cylinder retracts fully and the cycle is complete. This circuit is also used in pneumatics. This sequencing circuit appears on page 144 of your lab manual. The power unit is not shown to make the drawing look a little more simple. Instead of the power unit, we use supply emblems. Those would be the colored in arrows on the left hand side. Arrow pointing toward the supply manifold, indicating it's coming from the pump. Arrow pointing toward the power unit, indicating it's headed back to the reservoir. The chief elements of this circuit include a manually operated DCV, two normally not passing sequence valves listed as number 1 and 2, a pressure reducing valve in the lower part of the circuit, and a pair of double acting cylinders. The sequence operation is the clamp cylinder extends first, and when it is fully extended and pressure builds, then the drill cylinder extends, and that's the extend phase. The retract phase is that the drill cylinder retracts first, then the clamp releases the part. Now, as you look at the circuit, when we want to extend the actuators, we push in on the lever, connecting port P to port A. When the oil comes out and hits the T-fitting, it splits off. It attempts to move upward, but that actuator cannot move because its flow path is blocked by a normally not passing sequence valve. Taking the path of least resistance, now the oil flow moves downward toward the reducing valve, and since it's normally passing, goes through the reducing valve, through gauge C, and into the cap end of the clamp cylinder. The clamp cylinder extends. Once the clamp cylinder is fully extended, the reducing valve will close to control its clamping force, which is shown on gauge C. The moment that system pressure builds to the limit of sequence valve number 1, sequence valve number 1 at the top of your drawing will open, allowing the drill cylinder to extend fully. And that is the extend cycle. To retract the cylinders, we pull out on the DCV. Now oil is fed from port P to port B, and oil comes toward the T-fitting. The T-fitting, it splits off and attempts to go toward the clamp cylinder, but it cannot because that valve is normally not passing. Therefore, taking the path of least resistance, it enters the drill cylinder first, causing it to retract. The drill cylinder retracts completely. Pressure then builds and backs up toward sequence valve number 2. It opens, and then the clamp cylinder retracts, and the sequence is complete. Now, the final exam for the lab is actually a combination of two of these circuits, so that normally after you have gone through chapter 13 and you are now ready to build the final exam circuit, you will have already built it in pieces. So if you can imagine looking at this drawing on page 144 and then merging it with the one on page 143, that gives you some idea as to the magnitude of this circuit. So your final exam circuit would have been a semi-automatic, fully functional clamp and drill machine. This concludes part 1 of chapter 13. If you have any questions, email me. Otherwise, you can move on to part 2.